Amcor is a global leader in developing and producing responsible packaging for food, beverage, pharma, medical, home, and personal care, among other products. Amcor works with leading companies around the world to protect their products and the people who rely on them, and improve supply chains through a range of flexible and rigid packaging, specialty cartons, closures, and services. With more than 230 manufacturing facilities, 47,000 associates, and more than 40 countries worldwide, Amcor has a revenue of $12.5 billion and sales each year. Company is focused on making packaging that is increasingly lightweighted, recyclable, and reusable, and made using an increasing amount of recycled content. There is a critical challenge in being able to successfully produce light-weighted parts, for which a wide variety of tests are performed throughout the 24/7 operations in each site to ensure product quality and operational efficiency. The purpose of this project is to establish three hypotheses on different scenarios to be tested, analyzed, and interpreted throughout the statistical tools learned throughout the course. In this case, we have chosen to mainly focus on the quality of finished products comparing specific variables that could or not be related with the end result. The main goal is to gather real data and translate to our Minitab software, so that with the usage of certain descriptive statistics, graphs, and methodologies, we can provide a recommendation based on the data that will be obtained. One of the core values of this company is the quality of products they offer to their customers. There's a fine reputation that has been a key element in building and maintaining long-term relationships with global leaders in the food beverage industry. We, as a team, believe that the implementation of this project could help Amcor identify any potential patterns between their operations and the quality of products, and this way be able to address any defects ahead of time and develop the proper procedures and mitigation plans to avoid this from happening. We have chosen to focus our project in the Chino, California facility. This is the largest site in the West Coast for the beverage business unit and one of the most critical plants in the network. They operate more than 30 production lines in a wide variety of products with millions of parts being produced 24/7 because it is practically impossible to test every part coming out of the machines. The plant relies mainly on statistical data to monitor quality, taking a certain number of samples and tests throughout each shift. We have chosen three different tests to analyze the relation between certain variables. We will use the raw data obtained of these checks and use it to figure out whether the level of crystallinity affects bottle shrinkage, analyze different bottle types and their top load capability, and finally determine whether there is a relation between bottle heights and volumes. Once the data is exported into the software and is statistically interpreted, we will provide a list of recommendations to the company as to how they can address these potential issues. Now, the project objectives will be focusing on analyzing the following hypotheses and using brazen raw data from certain quality tests and try to understand the behavior between certain variables in the product operations. The first objective will be if does the level of crystallinity in a bottle affects the shrinkage levels. The second objective on this project will be the bottle type has any impact on the top load capability. And the third objective is there any relation between the bottle height and volumes? Tests to be applied in this project, we will use the following test. Dispersion measures the population and sample, normal distribution, hypothesis testing, analysis of correlation between two variables, and ANOVA.
Due to the high quality demand of plastics for the manufacturing industry, there has been an emergence of quality control devices. These devices combine X-ray technology and optical inspection to scan the plastics at very detailed level. Some of the things that can affect the quality of plastics are metallic contamination, air voids, and agglomeration of fillers. Fillers are added to the plastic for numerous reasons, including lowering the cost and improve the performance. It is critical that the dispersion of the added fillers is as uniform as possible to maintain the same properties in all the plastic. Failure to create a good dispersed material can affect characteristics such as strength, stiffness, thermal conductivity, transparency, and some others. The tests conducted in this study were obtained by using micro CT scanning on compound granules that included 50% filler and 50% polymer. To quantify the dispersion quality, structural analysis was made on the tomography images. There are numerous values that were measured, including structural model index that indicates the presence of structures, the structural thickness, the structural separation, the linear density. The author presented the results in a graph that compared the two types of compounds. Another comparative graph was made with the total porosity of granules that was produced with and without ventilation. The graph presented the results that the porosity percentage was higher with ventilation than without. Another reviewed article was about an automated multi-objective optimization for thin wall plastic products using ANOVA. The article was about plastic injection molding and the importance that all the process parameters need to be fine-tuned to obtain the quality, quantity, and profitability desired by the manufacturer. The quality characteristics in plastic injection molding include warpage, shrinkage, weld line, sink marks, among others. For thin wall plastic products, one of the most important defects that manufacturers want to reduce is warpage. For the analysis, the author used multi-response datasheet, ANOVA, and F-tests to determine the significance of parameters as a 95% confidence level. For the paper, the plastic product analyzed was an air conditioning vent. The purpose of the experiment was to optimize the parameters to eliminate quality defects like warpage, weld line, excessive clamp force. The authors used the ANOVA data analysis to identify the most significant parameters, rank the importance of the parameters, and provide the optimal combination of parameters for the warpage, weld line, and clamp force. ANOVA shows the best combination of factors and provide optimal combination of plastic injection molding parameters. The importance of parameters was presented as a percentage of contribution to each defect. Using warpage as an example, the melt temperature, the packing pressure, the mold temperature, and the cooling time play the most important roles.
As a project methodology, we have chosen three checks that are performed to bottles that are being produced. Number one is crystallinity. The polymer crystallinity can be determined with DSC, a technique that measures heat flow into or out of the material by quantifying the heat associated with the melting of the polymer. This heat is reported as a percent by normalizing the observed heat of fusion to that of a 100% crystalline sample of the same polymer. So our analysis will focus on whether the crystallinity percentage is related to the bottle shrinkage. Number two is the top load, also known as a column crush. The top load test ensures that the products consistently meet requirements for actual load. So our analysis will compare hot fill and cold fill products through their top load testing. And finally, heights and volumes. This is a common test in the plastic industry. So our analysis will focus on whether there's a relation between the bottle heights and volumes post-production. Does the level of crystallinity in a bottle affect its shrinkage levels? This is the first hypothesis we're testing. We started off by formulating the descriptive statistics of the two variables, crystallinity and shrinkage. There were 30 observations for crystallinity and 30 for shrinkage. You can see the detail in the attachment. We then generated the frequency distribution table to see if there were any specific patterns followed by these test results. In the crystallinity side, it was noticed that 30% of the observations were within the values of 21 and 22. As to the shrinkage, 30% were between -1 and 0. Considering a 95% confidence interval, we used the histogram and the box plot to graph the test results for both variables. It was noticed that the crystallinity had a slightly left skewed distribution and that the shrinkage is nearly a normal distribution. After further analysis, we believe that the outlier in the crystallinity graph created enough noise to the distribution, with it just being a single value that is off. We can consider this as an abnormality and confirm that both graphs follow a normal distribution. By looking at the correlation graphs below, we can conclude that there's a direct relation between these two variables. The higher the crystallinity, the lower the shrinkage level. Again, there is an outlier, which we have decided to ignore for the purposes of this analysis. To complete this analysis, we use the ANOVA. Considering a significance level of 0.05 and a p-value of 0.112, we will fail to reject the null hypothesis. In other words, we have accepted the null hypothesis and rejected the alternative meaning that our conclusion is that the bottle crystallinity has a direct relation with the bottle shrinkage levels. The second hypothesis is, does the bottle type have any impact on the top load capability? To test these hypotheses, we started off by formulating the descriptive statistics of the two variables, hot fill and cold fill bottles, which you can find on the tables below. There were 40 observations for hot fill and 40 observations for cold fill. We then generated the frequency distribution tables and noticed that 40% of the observations for hot fill were within the values of 88 and 92, and 65% between 70 and 80 for cold fill. Considering a 95% confidence interval, we used the histogram and the box plot to graph the test results for both variables accordingly. The hot fill was normal distributed, however, the cold fill looked to be skewed to the right. There were two outliers that caused the graph to shift as it did, but we have decided to consider this as an abnormality, as the box plot also shows that the data is mostly concentrated within the second and third quartile. By looking at the graphs, we can't really conclude whether there's a direct relation between these variables, as the data is completely scattered throughout the graph. We will then rely on our next analysis of ANOVA to come up with a conclusion. Considering a significance level of 0.05 and a p-value obtained of 0.746, we will fail to reject the null hypothesis. In other words, we have accepted the null hypothesis and rejected the alternative, meaning that our conclusion is that the bottle type has no relation with the top load capability. Finally, the third hypothesis. Is there a relation between the bottle heights and volumes? To test this hypothesis, we started with the descriptive statistics, followed by the frequency distribution tables, and notice the following. Considering a 95% confidence interval, we used a histogram and box plot to graph the test results for the height and volume. Both graphs show a normal distribution of the observation and no outliers. By looking at the graphs, and specifically the fitted line plot, the red line formulated by the software shows a slight tendency of the observations from larger volumes and taller bottles. However, there's not enough data to conclude that there's a strong relation between these variables. Considering the ANOVA and a significance level of 0.05 with a p-level obtained of 0.709, we will fail to reject the null hypothesis. In other words, we have accepted the null hypothesis and rejected the alternative, meaning that our conclusion is that there's no direct relation between heights and volumes. After all this analysis, we can conclude the following given the hypothesis results we were able to obtain. Number one would be that the higher the crystallinity levels, the less the shrinkage in a bottle. Number two would be the bottle type plays no difference in the top load capability. And number three would be that there is no direct relation between the bottle height and volume capacity. So our recommendations to Amcor would be the following. Produce bottles with higher crystallinity levels to avoid shrinkages. Maintain the same test procedures for hot fill and cold fill bottles. And number three would be perform separate tests for volumes and heights.